let us simply look at another key topic, the simple regression analysis. Here, let us we briefly discuss what regression analysis is all about, but our interest is on type of variables we use in regression analysis and how linear regression analysis is all about. So before we dive into types of variables, what is a regression analysis, for instance? So regression analysis is just analytical techniques that relate two or more variables. Analytical techniques that we use to test how much relationship is shared by two or more variables. When you are talking of two variables, we are talking of a simple regression analysis. For instance, if we have variable y and we have variable x and we want to know their relationship, so we could use any distribution or statistical test to check that. Conventionally, we run t-test to know if y and x related in any way, and in doing that we are doing what we call regression analysis. Regression analysis is quite little different from correlation analysis. Regression analysis is all about the relationship, but correlation analysis move ahead to check the degree of relationship between these two things. So in regression analysis, we have what we call the dependent variable and we have the independent variable. When you have a dependent variable and one independent variable, you are doing simple regression analysis. But a situation where you have more than one independent variable against a dependent variable, we are talking of multiple regression analysis. So in most cases, we deal with linear relationship in order to avoid some complex analytical means. So having discussed about regression analysis, let us look at the types of data we analyze in regression analysis. Data here is sometimes called variables. So we have different types of variables we analyze. Variable is the information we want to check the relationship. Here we have categorical variables or data. We have dummy variable, we have nominal variable, we have integer, we have ordinary variable, we have numerical variable, and so many. But let us quickly go to them one after the other. We look at categorical variable. In categorical variable, what type of variables do we classify as categorical variable? Categorical variable is always qualitative variables. Qualitative variable in the sense that they are just qualified. We use some certain measure to qualify them. They are not measurable. For instance, if we talk of gender is male or female. We may use F for female and M for male. So these are qualitative or categorical variable. We just categorize this as a male and categorize this as a female. So in this case, they are not quantifiable. They are only categorical variable. But if we go down to check the next one, dummy variable. Dummy variable here is a situation where you want to nominate a quantitative variable into a categorical variable. For instance, we say the gender. We have male or female. For you to apply dummy variable, it means you are going to nominate some numerical value to represent male and numerical value to represent female. So normally in analysis in statistics, we use maybe 0 to represent female and 1 to represent male. In this case, you are no longer talking of categorical variable, but you are talking of what? Dummy variable. Dummy variable is that you've represented the categorical variable using numerical figure. So the next is nominal variable. Nominal variable. As the case may be, nominal variable are always non-negative variable. They may be integer, but they are non-negative. For a variable to be nominal, it must be non-negative. So the next is an integer variable. Integer variable is sometimes a point variable, a discrete variable. It must not have fractions. So they are just variable. For instance, if you say age of a person, neither the person is 1 year or the person is 2 years. So all this 1.5 years, it doesn't matter. So for you to be an integer, it must be here. For instance, we could as well describe relationship as maybe red or green, black or blue. Christian, just categorically, in an integer is just a point, a straightforward measure. So the other one is ordinal variable. Ordinal variable. Why is it ordinal? Ordinal variable is that it is a qualitative variable, but we order them in order to be able to measure them. That is why we call it ordinal variable. For instance, if we say religion, we discover that we could classify religion into form or more than four. We say, okay, let us have Christianity, or have Muslim, or have traditionalists, or have Hindus, depending on your classification. So in analysis, we could say, okay, I'm nominating one to be Christian, two to be Muslim. So all this, you are ordering them. You are ordering them. Also, you can do something, you order them A, B, C, D in order to be able to have them in analysis. So that is how ordinary variable comes in. So the next we'll have a numerical variable. Numerical variable are all scale variables. They are numerical. They are measurable variable. Another name is quantitative variable. They are numerical. So it's opposite qualitative variable or all these categorical variable. So we have another one, continuous variable. Continuous variable. It can appear as a fraction in reality. So, but continuous variable are variables that are infinite. They are infinite variable. They are continuous. They are continuous. They don't have bound. For instance, if we say that I runs from 1 to infinity, it's a continuous variable because infinity could go as long as anything. So, in such case, you are talking of continuous variable. But another variable called discrete variable. Discrete variable here is that it has upper bound. For instance, we could say that I run from 1 to 5. So it's a discrete variable. It has a boundary. It has the lower bound. It has upper bound. So it's different from what we call the continuous variable. So these are different types of variables we use in analysis. There could be quantitative and there could be what? Qualitative. As we've said before, we've discussed what regression is all about. That is just an analysis we use for relationship between one or two variables. So in determining this relationship, we normally look at the variations. The variation. For instance, if we say that y is related to x, the question is at which variation could change in x influence the change in y. So here we look at the variation. That is why we have something like the coefficient of multiple determination when we are talking of multiple regression, or coefficient of determination when we are talking of simple regression. Coefficient of determination, which we normally call R square, try to check the percentage of variation that the independent variable was able to explain about the dependent variable. Whenever, for instance, you have your R square to be let's say 0.91, it means that your explanatory variable, which is the dependent variable, we are able to explain 91% variation in your dependent variable. In such case, it means also that 9% of the variation in the dependent variable was unexplained in that regression. And this as well is one of the measures to check the fitness of a regression model, because regression model is all about fitting a regression line. Remember that in regression analysis we use sample estimate to represent the population estimate. The reason is because it is very hard for you to examine the population estimate. So in using the sample, the question is how much of the relationship in the population estimate that your sample estimate were able to fit. So the closer the fitness of your regression, the better the result. So regression is all about fitness. So simply in regression analysis, we could have that y is a function of x, and that is a simple regression. So, but things that are key when you are, specifying a regression model is that there are other parameters that is not a coefficient of unexplained parameters. That is the intercept. Sometimes we call it the constant, and the error term. The constant here represents a constant factor. For instance, if we say that weight affects education, it means that anything outside weight, nothing else affects education, if we only believe that weight affects education. But in regression analysis, there's a chance, there's an opportunity that beside weight, there are other things that could as well affect education. And because we are interested in seeing the component of weight effect on education, we subject every other thing into the error term. So that is the reason why error term is key. All the assumptions of estimation techniques that we use in regression analysis all boil down to error term. The linearity of the model is close to error term. The constant, the heteroscedasticity, and so many of them is boiled down to error term. So, but the constant term means that even if you remove the weight, there are other things that could affect in constant, conditions. So that is the constant term. So when you have simple regression, you have one independent and one dependent. But multiple regression, you have so many independent but one dependent variable. So that is all about the simple and multiple regression analysis. Let us go further. So here we have some fundamental conditions in regression analysis. So first of all, we test the parameter. The parameter is to know how much changes in x that is imparted in y. So the parameter is always that variation in x or in the independent variable that we could say that normally in statistics we always interpret that a percentage point change in the independent variable will yield so percent change in the dependent variable. So the parameter helps us to measure those changes that are the variation. So we have homogeneity or variance or heteroscedasticity or variance. In regression analysis, that is why I said that the error term is key. The error term is key. Here we are talking of the constant, the errors of all those variables. Are they constant over time or they varies all over time? So one of the fundamental rule of OLS, ordinary least square, that is the conventional measure of regression analysis, is that all the error terms that accumulated to the bigger error term in regression must have constant variance. So they must not vary over time. So their variance must be unity. So in a situation where they have wider spread variance, it means that the fundamental of regression analysis has been violated and the result obtained thereby is biased. So we always take care of what? Heteroscedasticity. Heteroscedasticity is a problem in regression analysis. Rather, we fight to achieve what? Homogeneity in regression analysis. That all the variables, all the error terms in the regression must be homogeneous. Another one is independency of observation. Independency of observation here, we talk of multiple collinearity. In a situation where we have different variables that are highly correlated to each other, and you are bringing all of them inside regression analysis, you are committing dependency of the observations. So it means that your regression analysis is going to have relation of multiple collinearity. Another one is normality. We discovered that most of the time series data are abnormal. due to some seasonal variations and cyclic variations. So for you to have a good data to fit in linear regression analysis, you have to normalize it. You have to normalize it, removing all the outliers. Outliers is abnormal changes over time within a data set. You have to remove all those things. So one, you have to normalize it in order to fit in. So that is another thing. Again, we are dealing with linear relationship. Linear relationship. A situation where you want to, not all relationships are linear. So a situation where you want to examine a non-linear relationship into a regression model, it means that some estimators, something like ordinary least square cannot work. So you need to go for higher estimation. So we do our linear here, linear in parameter mostly. So here some assumptions of regression analysis. Assumption of the regression analysis itself has no assumption, but the assumption here comes from the estimator we apply in estimating regression analysis. So some of the assumption here is that there must be linearity in the relationship for us to, we use OLS estimator, for instance. There must be linearity, there must be homogeneous, there must not correlated, that is the multiple correlation. There must not be correlated in the editing, and there must not be auto-correlated too. So auto-correlation is a situation where some key variables are correlated with the error term in that model. So all these are so many assumptions. So again, the mean score must always be 0, that the estimated mean must always be 0. So these are so many assumptions. So for you to achieve a good fit in regression analysis, most of these assumptions must be upheld. So we move ahead. They must be upheld. So these are some fundamental things we check when we are dealing with regression analysis. The next one is how to perform simple linear regression analysis. Simple. In performing simple regression analysis, the first step is for you to formulate the model, specify the model, specify the model. Here, we take a precaution. In specifying a model, you have to specify a model that will be fit in estimating the analysis. Sometimes you overestimated a model, what we call over-parameterization of a model. A situation where there is another law in regression analysis that says that even though there may be so many variables that may affect your dependent variable, that it is very, very good that you be parsimmonistic. And being parsimmonistic in regression analysis is that you have to be conscious. You have to take the core variables that you are dealing with. In regression analysis, we have what we call the core variable, the peripheral variable, the control variable, and unobserved variable. So the main thing in any regression analysis is the core variable. So inputting control variable or peripheral variable is optional. So but that control variable must be in there. So if you specify a regression analysis missing a control variable, it means that there is an error in that specification, and that is what we call misspecification of a model in regression analysis. So one, your regression specification should not suffer from omitted variable bias. Omitted variable is where you omit the core variable in your regression analysis, and you must not over-parameterize. When you over-parameterize, the key variable you want to know the impact, you will miss, because some of the impact will be swallowed by unnecessary variable you added. So these are so many ways you could perform. But we've discussed it that in regression analysis, we have one dependent variable and one independent variable. And we have the intercept, which is the constant that predicts the value of dependent variable when the independent variable is 0. And we have the x. Sometimes we use x to represent the independent variable, and we use beta to represent the coefficient. Beta 1, it could be any other symbol. It's not only specified or unique to beta 1. It could be any other symbol to represent the coefficient. And we have error term component of the regression. So we will say that in regression analysis we have the dependent variable, the independent variable, the coefficient, the constant, and the error term. So these are the components of the regression analysis. So far so good. We've been able to discuss regression analysis, types of regression analysis, types of data we apply to regression analysis, the important, how do we perform regression analysis, what are so many challenges, and we've been able to observe that all the components of regression analysis, and we're able to discuss later about the techniques.